Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to our NPTEL online certification courses on engineering drawing and computer graphics. I am Rajaram from Mechanical Engineering, IIT Kharagpur. We are in module 1, lecture number 6 on introduction to engineering drawing. In today's class, we will briefly look at special dimensioning thing and also tolerances. Textbook what we are following is Engineering Drawing by N.D. Bhatt. On special issues on dimensioning, in the last class we tried to look at different ways of dimensioning it. For example, if it is a cylinder having multiple steps, so that on the other side of the view we look it like a step 1. Try to look at diameters. If it is diameter, we use symbol phi and smallest one inside and the largest one outside. That is the way we try to look at. So, they should be dimensioned by their diameters, especially should be dimensioned in the views that they appear as rectangles. So, if we have multiple cylinders, such kind of thing. If we are looking from this view, they appear like rectangles. In that case, diameter we are going to show it in this way. We do not usually show diameter in this view, everything supposed to be from this one. So, these two are of same dimensions. Similarly, this one of same dimension. Similarly, this one and this one is of same dimensions. So, this is what we call one of the view, front view, and perhaps this one is the side view. If there are anything like tapered features, for example, here we have a tapered feature. Instead of having a rectangle, perhaps the object might be having such kind of feature. In that case, we show its height and also we show its length, 20 units and 60 units. Giving height of one side, distance between flat ends and their taper slope using a flat tapered symbol, we usually go for tapered features. Here we are showing these dimensions and also something like a tapered one with a symbol of tapered shape. This is the way we show, and this taper perhaps increasing in that ratio. This is the way any taper things we go ahead and show it. The other way is, let us look at this one, giving the height of one side, perhaps this one, length of taper and slope of the tapered face. So, length of taper is this 60 units and this is the taper, this is the taper, and it makes an angle of 60 degrees with the horizontal. So, that way also we can really show it, one by giving how this taper symbol ratio is going to change, the other way is through slope and angle. These are two ways of special dimensioning. Similarly, if we have threads, screws and so on so stuff, we do not straight away, for at least for drawing, we do not put threads directly on that. for dimensional purpose and other things, we show particular dimensions in that way. When you see such kind of things, these parts, that indicates that these are threads. For example, if you are taking a pen which can be opened into two parts, it always be having screw and thread kind of combinations. So, one of them perhaps may be having external threads. If you are taking Reynolds pen, the frontal part, if you are unscrewing it, it always have threads on that blue color portion. So, those threads what you call external threads. Similarly, for the same Reynolds pen, inside of that white color portion, you will have threads inside of that kind of things are called internal threads. So, when you are showing these dimensioning for bolts, nuts, pen screws, caps and other kind of things, there always be external threads and internal threads. So, there are different ways of showing these internal threads and external threads. More details we will learn in the future classes about that. But whenever we see this kind of rectangular portions, a tapered ones and a kind of slight curve and lines, it indicates that it is supposed to deal with threads. And usually these threads by metric M portions we will show. The metric threads, for that purpose there is a symbol M. Perhaps it might be having a diameter of 12 mm. So, if it is external threads, we show it from the external side. This is the thread on which we have it. So, M12 we will show. If it is something like the white color portion of the Reynolds pen, which is having internal thread, then in that case internal portions we are going to show it. Similarly, whenever these threads, bolts, nuts and other kind of things are involved, we usually go with depth of the drilled hole. For example, for this object, inside there is a hole in which you have a thread. So, depth is always be required. For example, here in this case 12 mm. So, from one end it is shown 22 mm, this one. So, from here it is 22 mm up to this portion. And thread, perhaps the object size is up to that, hole might be created up to this level, but threading is done up to this level only. So, then in that case the thread length 18 mm also has to be shown. This is the 18 mm. This is the way threads and special screw features we will show it. We always show is different views like frontal view and side views, because it is a thread kind of thing, external thread. If you are looking from this side or perhaps from this side, it looks like a circle on which we start seeing the threads. So, in that case we have inside dimension also. More details we will learn about that in the future classes. Usually we go with the symbols for any kind of dimensioning. By just looking at that symbol, we will be in a position to understand whether the drawing consists of diameter or spherical diameter, radius and so on. If we are using phi, it represents diameter. If it is something like S phi, it indicates that spherical diameter. For radius, we go with R, and for spherical radius, we go with SR symbols. If these are square components, we use symbol squares. Sometimes we might be going to represent cylindrical objects. In that case, we use CYL as cylinders. Similarly, whenever these multiple holes are made on a plate, there will be a pitch diameter represented. In that case, we usually go with this PCD, pitch circle diameters. If things are equispaced, we go with EQSP, equispaced kind of things. Similarly, other things like if it is conical taper, we use it in that way. If it is just a flat taper, we use it in this way. something like flat taper symbol is this. If it is conical kind of taper, we use this one. Many other things like typically for threads and other things, we usually see these symbols M, that means metric thread, one way of creating these threads. There are variety of holes and so on, so things like counter bows, counter sinks and so on. There are special symbols, people usually use it. So, on drawing sheet, symbols, dimensioning these units are the most important thing if you want to convey a picture to machinist. Now, all these dimensions for drawing is perfectly fine, like saying 12 mm. But if you are asking a machinist to prepare 12 mm kind of object, perhaps it can be length, it can be hole, it is not possible to precisely make 12 mm. There will always be plus or minus deviations possible because we are dealing with machines. There are many factors which influences this machining. For example, I would like to make a turning operation where a cylinder of 20 mm I would like to make, but a small deviation because of mechanical vibrations, temperature variations, or the way how we feed this lathe machine and so on, so things, there is always chance that it might be excess, it might be low of that object. Many factors influence these things. So, 12 mm or 20 mm usually is not a good idea to indicate. It is always good to mention 20 ranges to 20.5 mm and also 19.5 mm, or perhaps something like 20 plus or minus 0.05 mm. Such kind of dimensions what we present are called tolerances. Let us learn more about these tolerances. The basic definition for tolerances, it is an allowance for a specific variation in the size and geometry of a part. No object will be made with precise size and also shape in a repeated way. If you want to repeat it, multiple objects you would like to create, there will always be variations within that. So, it is not precisely possible to make the same object of same size and geometry. So, tolerances set allowable variation. So, any quality inspections and so on, for that purpose these tolerance limits are strictly imposed. If there is a large variation, it may affect the functionality of the part. For example, the thing what we have taken, a simple Reynolds pen if we are taking, it has both the screw and the other part. So, when you are trying to screw this Reynolds pen, the blue color part, if the thread is too small, it immediately loosens that pen and the functionality of the part severely affects. Perhaps if that thread is very large, perhaps it might not really fit into that object also. So, a large variation always affects the functionality of these parts. Even for example, the finger rings what we use, if it is too large, we will not be in a position to effectively use that ring. If it is too small, it does not fit into our finger also. So, any object whatever you take with these tolerance things, if there is a large variation, it severely affects functionality of the part. However, if you want to really make it precise, that means you are going to make very small variation, then one has to be at most care, and to make that component it will be very costly. So, one has to carefully play with this small variation to large variation, so that on one side it will not increase the cost. This cost can be time consuming, it can be in terms of monetary things, in terms of production, how many quantities you would like to prepare it, that also costs, and many things. So, usually industries try to optimize the small variation and large variation. Tolerances, when are they important? Let us look at a standard example. For example, in machining mechanical engineering, we call few things as assemblies. These are individual components, you fix them so that finally it makes like a product. Let us pick an example like spectacles. This is an assembly. This consists of the typical glass, perhaps the frame, this is the frame, perhaps there will be joints, those joints might be having screws, glass, screws and frame. These are called parts of this spectacle. When you club them in a proper way, you will be in a position to get an assembly. That assembly makes the functionality like spectacles. Now, let us look at the individual thing. In that frame, this is the frame, we will like to put a glass. Let us make this glass. This is the glass what we would like to fit. If this dimension, let us look at this dimension, if this dimension first of all is not easy to prepare the same dimensions. Even if we make it a small variation in terms of fixing it like mechanical stresses, perhaps might twist it. So, the main functionality like fitting this glass inside that, we may not be in a position to achieve it. A small increase in mechanical stresses, perhaps temperature variations or perhaps surface abrasions and other things, it may severely affect the functionality of that. But in case if we are going to make it a smaller one, this is small size, but this one large, it just comes out of that object. If it is too large, if this one is large and if this one is small, it can't really fit into that. So, parts will often not fit together if their dimensions do not fall within a certain range of values. For example, let us consider this dimension is 25 mm. This one 25 mm is correct fit. Perhaps when you are making, this is ranging from 25.1 mm to 24.9 mm within that range. If this one is 25, it fits in that object. If it is 26, definitely it will not fit into that object. One has to do other ways of trying to fit that. So, parts will often not fit together if their dimensions do not fall within a certain range of values. For example, you broke your one of the glass, you would like to replace it. This one you would like to replace it. If a replacement part is used, it must be a duplicate of the original part within certain limits of deviation. So, when industries make these kind of products in multiplication, many parts, one has to be very careful with these tolerances. Repetition is very much required because you broke it and you would like to replace it. So, to replace that, you require similar kind of component of precise dimensions. If it is not possible, then something one has to play with these tolerances. It is a common practice, cost generally increases with smaller tolerances. Small tolerances cause an exponential increase in cost to make it. Parts with smaller tolerances often require special methods of manufacturing. is not only about cost. If you are going for very small tolerance values, to prepare that itself we require special equipment. Parts with small tolerances often requires greater inspection and call for rejection of parts. How much care we might be going to take to create such kind of small tolerances? End of the day, it has to go through inspection. A small deviation from the required tolerances, there is a high chance that part will be get rejected. So, small tolerances always have a greater inspection thing, and high is a highly likely that many parts will be rejected. Though it is a good practice to have smaller tolerances, but making that itself is challenging. These tolerances we specify it in different ways. For example, it can be based on size, it can be based on geometry also. For size, let us look at it. It limits specifying the allowed variation in dimension. That means, it can be length, width, height or diameter, etc., given in the drawing. These kind of things, if we are talking about, those are about size tolerances. Regarding geometry also, we talk about these tolerances. For geometric tolerancing, it allows for specification of tolerance for geometry of the part separate from its size. I want to draw a rectangle, but perhaps there is a small variation, it might look like trapezium kind of thing. These variations are very small. Such kind of thing, instead of having a square, perhaps this trapezoidal kind of thing is also tolerated, and that is what we call geometric tolerances. In terms of lines, lengths, diameter, that kind of thing what we call size tolerances. As I said, we would like to draw, we would like to prepare something like cylinder, but it might look like slightly oval. That kind of things are also geometric tolerances one has to maintain. Geometric dimensioning and tolerancing uses special symbols to control different geometric features of a part. Though we are clearly mentioning it in terms of size like width, height, diameter and so on, perhaps a circle, two slightly ellipse or oval kind of things, we use special kind of symbols. That means, it is allowed up to that level. The tolerance for a single dimension may be specified with dimension and the tolerance. We will shortly look at it, how to represent that. One thing what we have to notice, the tolerance is a total variation between upper and lower limits. If I am saying something like 25 mm, on upper side up to which level I can really go, on the lower side up to which level I can really go with that dimension. Is it 24.9 or is it 24.99 or is it something like 25.01 or is it 25.1? Such kind of upper lower limits, something to deal with this total variation. Let us look at an example. Here we have a drawing sheet on which there are many components mentioned. For example, it is for a turning operation, the chuck, screws and other things here is represented. For example, let us pick this one. We can see that something like phi representing diameter 1.375 units with plus or minus 0.005 units. Similarly, let us look at this one 1.120 plus or minus 0.005. Similarly, let us look at this diameter phi 2.75 plus or minus 0.02. So, when machining is done and perhaps product comes out through this engineering drawing sheet, When it goes to quality check, mainly quality control guys check whether these tolerances are met or not for that object. If someone measure the diameter of that outer circle, if it is 2.75, perfectly fine. If it is something like 2.77, that is also perfectly fine. If it is something like 2.73 units, that is also perfectly fine, because this plus or minus 0.02 represents. If anything 2.78 or perhaps 8, if they found it, they will reject that part. So, for that purpose these tolerances are always be helpful. Similarly, let us look at this one. It is not necessary that you always have plus or minus 0.02 on positive side and negative side. Sometimes on positive side it is preferred, but not on the negative side. When you want to fit the things and so on, if it is lower than that, it may not hold the object, it will be very tight kind of thing. Anything above, for example, if this is the object, in that I would like to put a cylinder. Now, when I am going to measure this dimension or perhaps this one in a more appropriate way, if I want 25 mm for that, anything above 25.01 is preferred, but if I go below 25.1, it will be somewhere here around. So, this cylinder cannot be entered into that object. So, sometimes these lower dimensions supposed to be strictly imposed like 0. Anything above is perfectly fine if it is that kind of objects. For the same thing, if we are talking about cylinder which has to be fixed in this object, if I am going with that 25 mm here, this is fine, perfectly fine, but anything above that, maybe 25.02, it will be out of that box. So, we can't really fit it. In that case, what we will do is lower side is preferable, upper side is not preferable. So, based on that your plus and minus variations always happen. And these tolerances are broadly divided into two parts. One is limit tolerances, where we show the dimension 2.5, 2.45, both the things. Similarly, limit tolerances for which limits are mentioned, it can vary from 1.4 to 1.5. This diameter can vary from 1.5 to 1.75 and so on, so things. Similarly, the angles 28.0 to 28.4, such kind of limits if we are showing, that is called limit tolerances. If it is plus minus kind of tolerances, we usually show it in terms of 2.5 plus or minus 0.0 minus 0.05. Such kind of thing, a common practice, we see it on drawing sheets, something like 1.45 plus or minus 0.500, something like plus 0.15 minus 0.10. Such kind of things what we call plus minus tolerances. So, to summarize our introduction to engineering drawings, we first looked at drawing sheets, drawing instruments, lettering, layouts, complete picture on dimensioning, tolerances in the first 6 lectures. In the next class onwards, we will learn about how to draw lines, curves, bisector lines and so on, how to utilize these instruments to construct geometrical things, how to construct common conic sections like parabola, circle, hyperbola and other curves like cycloids and so on. So, in lecture 7 onwards, we cover these conic sections and geometrical constructions. Thank you very much.